And I'm Captain Miles.
And we did our STEM project on establishing a population of oysters on the list. So we decided to look into oysters because in the Chesapeake Bay, there's been a huge population decline. And this is a problem because oysters filter the water, and they also provide habitat for other creatures. So it affects the whole ecosystem and not just the oysters. So our first project idea was to grow diploid and triploid oysters. And triplet oysters have 3 chromosomes, so they grow faster and are more disease resistant. However, there's already a study done on these, and they said that they would not be safe to introduce into the bay. So then we wanted to look at diseases such as MSX and dermal. However, oysters are already becoming more naturally resistant due to natural selection, and so we didn't do that. Then we thought about looking at the plastic microbeads. However, before doing this, we had to set up a tank and just get the oysters, which led to our hypothesis that by monitoring and regularly mating the variables in the tank, the population of the oysters would naturally stabilize.
Our biggest priority was to just get the oyster tank set up. So our first step was to find a suitable tank, which we luckily found in North Hall. The second step was to order supplies. This included circulators, substrate, which is the material on the bottom of the tank, and testing equipment. So on the left here is a salinity refractometer that measures the levels of salt in the water, and on the right is a nitrate-nitrite test kit, which we'll talk about in a little bit. The third step was to meet the oysters' habitat requirements. Oysters have certain requirements that need to be met in order to ensure their survival. So these include salinity having to be between 14 and 21 parts per thousand, and substrate having to be on the bottom of the tank. Once the tank was ready, we purchased a dozen Chesapeake Bay oysters from a seafood market in DC. They were put on ice during the bolus, and 11 out of the 12 oysters purchased were introduced to the tank. One of the oysters we did not introduce because it had other organisms growing on its shell, and we thought they would interfere with our test results. Another thing we have to keep in mind is that oysters are marine animals. They excrete ammonia as a nitrogenous waste. Ammonia is very toxic. This is not an issue in the bay because the bay is such a large body of water that when ammonia is excreted, it is in such a low concentration compared to the body of water. But when you put 11 oysters in a small tank, the concentrations can build up quite quickly. So in order to prevent this from happening, we introduced nitrifying bacteria to the tank. We introduced 2 types. The first type converted ammonia into nitrite. However, nitrite is still a toxic compound, so the second type converts nitrite into nitrate, which is a less toxic compound. The bacteria was introduced at the same time as the oysters, and then the oysters were fed using rehydrated phytoplankton. The last step that we had to do was to keep track of the tank and the variables. The variables included salinity, dissolved oxygen, pH, nitrate, nitrite, temperature, and a couple more. We performed tests, and the levels and observations were reported daily. Another variable that we had to keep in mind was the amount of oysters that were alive. How you can tell if an oyster is alive is by checking for life signs. So if the oyster's shell is open and it closes when you touch it, then it is alive. If the oyster shell is tightly shut, then it's also alive. But if the oyster shell is open and it does not close with the stimuli, then it is most likely dead or dying. This is a video of the generalized test. You can see the opening in the shell right there, and watch it as it closes. Right. If an oyster is found to be dead, it had to be removed immediately. Unfortunately, 2 of our oysters, that's Pearl and that's Marina, they both died, and Marina we didn't catch early on, and she decayed in her shell, but we were luckily able to remove her from the tank safely. Pearl we caught early on, so she was very easy to remove. To organize our data, we gathered all the measurements of each of the variables and put them in tables and graphed them on time plots. To prove that our hypothesis was successful, we variables that stabilize or not. And when something is stable, it's not changing. So we decided to calculate and graph the rates of change in each of the variables. Up here is the two graphs of salinity. So the top graph is the time plot, and the bottom graph is the rate of change graph. So the rate of change graph shows you that it stabilized by around February 14th, and the top graph shows that it stabilized to 17 parts per thousand. And these are some of the other variables that we graphed. These are their time plots. This is dissolved oxygen, nitrate, nitrite, and temperature over time.
So the hypothesis was supported because over time, all of the variables, the rate of change reached zero, and the ammonia levels were consistently at zero. So looking at trends for salinity and nitrate, they both stabilized by February 14th. And then for nitrite, temperature, and dissolved oxygen, they stabilized by the 14th, and then they fluctuated again and stabilized finally by the 25th. So this led us to believe that from February 6th, when they were introduced, to the 14th, the oysters stabilized, but from February 6th to the 25th, that's when the bacterial population finally stabilized, because that's when the nitrite stabilized, and that's the byproduct of the bacteria. And the ammonia levels were consistently at zero, so that meant that the tank was stable.
Throughout this year, we learned that this is a trial and error process. Up here, you can see this is our timeline with each of our project ideas. On the bottom, with the green lines, they represent each of our ideas. On the top, with the red lines, these represent each of the roadblocks that we hit. But even with all these roadblocks, we were able to find and complete a successful and intriguing project. There are 3 important skills that the capstone has left us with. First is problem solving. We learned and used this skill when navigating our way around roadblocks. The second is knowing when you need help. The capstone involves a lot of independent work, and it is sometimes easy to get stuck and only see your project in one way because that's the only way you can see it. So it's helpful to know when you need to reach out and gain a different perspective to keep your project going. The third and final one is presenting and reaching out. When you start the capstone project, you're looking into a topic that you know little to nothing about, and it is a part of the capstone is reaching out to experts in the field and the surrounding community and gaining their insight on your project and seeing what projects they're doing and seeing what's current in your field of study. Also, throughout the year, we practice presenting on a topic that we know a lot about, and that really helps us develop our presentation skills. Overall, the STEM capstone has taught us so many valuable life lessons and skills that prepare us for future research, college, and beyond. And I'd like to take a moment to thank Ms. Darling, Ms. Nutter, and Professor Tara Stoley at George Washington University for all of their help. Thank you.